Okay, let's continue our discussion on limits with two topics that really go hand in hand. We've got continuity and one-sided limits. And let's start with continuity. Continuity just means, or whether a function is continuous or discontinuous. Basically, it means can you draw the whole thing without lifting up your pencil? Or are there locations on the function where you would have to lift up your pencil in order to continue drawing it? So an example of a continuous function would be a sine wave. The sine wave, cosine, sine, they go on and on forever, and you never would have to lift up. And I mean, obviously it goes to the left and the right forever, but at any portion of that graph, there are no breaks, there are no holes, asymptotes, jumps, anything like that. A discontinuous function would be like a tangent. A tangent curve has this little curve, and then I would have to pick up my pencil, go to the other side of an asymptote, and draw the next one, and so on and so forth. A continuous function, polynomials are continuous. Polynomial functions like a cubic. There is no place on a cubic where you have to pick up your pencil to continue drawing that function. An example, a non-example, or a discontinuous example would be anything with a hole in it. We talked about when we were talking about limits before, limits that have hole or functions that have holes, and if that function goes on this way, I can't draw this function, the whole thing, without picking up my pencil to fill in this dot right there. So if it could be defined at that point, but still I would have to lift up my pencil. So a hole makes it discontinuous. A square root function, that's continuous everywhere to the left of, let's just make this y equals the square root of x. This is not continuous everywhere. This is continuous on the interval 0 to infinity. It's kind of like when you had to tell what are the domains, and a lot of times the domain might be the places where it's continuous, but it's continuous where it's defined. It starts at 0, and there are no holes or breaks moving to the positive side. It just doesn't exist on the left, so it's only continuous. And a lot of questions, as we'll see in a minute, are discuss the continuity. This one, I'm double thinking whether I should have put it on which side I should put it on. It's not continuous everywhere, but it is continuous where it's defined. I want to do one with a hole that is not defined. It's undefined at this point, also not continuous. So jumps, discontinuities, holes, asymptotes, those are all things that make a function not continuous. So here's an example problem. Discuss the continuity. And this is a picture that I just made up. These might be a function that's given, and you have to kind of know what the graph looks like. In this particular one, I'm giving you the picture. So this thing is continuous on all the places, basically where the discontinuities don't happen, where the holes and asymptotes are not happening. This thing is continuous from negative infinity. There are different ways you can write this interval notation. You might use inequalities. I'm going to use negative infinity to negative 4. And I'm going to use round parentheses because it's not continuous at negative 4, but it's continuous everywhere up to negative 4. Then it's continuous from negative 4 to 0. And we have an asymptote. It resumes on the other side of that asymptote, and it's continuous from 0 to infinity. I made it kind of weird. It's got this funny shaped point right in here, but that's not a discontinuity. I can draw up to that point and keep drawing without lifting my pencil. So there's an example question on discontinuity. Okay, so now let's get to the other topic, one-sided limits. That's what we're going to talk about on this particular slide. So here's an example function. It has two discontinuities. It has a discontinuity at negative 5 where we jump, and then it has a discontinuity at positive 5 where the function is defined at another point. So we have a hole in the graph. So let's connect this all to limits. So first of all, the limit, a one-sided limit is noted with these little plus and minus signs on the negative 5. This first one says the limit as x approaches negative 5 from the negative side or from the left. We indicate that we want to talk about approaching it this way with that little negative sign. I'm coming from the negative. So as I follow that green arrow towards negative 5, I am getting closer and closer to a height of 3. All right? As I follow from the right, that little positive means I'm coming in this way. That's what this little positive means, from the right. As I come into that graph from the right, my height is getting closer and closer to positive 1. And we've seen when we talked about limits that don't exist, we saw pictures like this, but at that point we just said the limit does not exist. That would be my putting it all together. The limit does not exist. So all of this is discussing what's going on at x equals negative 5. The limit from the left is 3. The limit from the right is 1. The limit does not exist because the limit from the left has to match the limit from the right in order for the limit to exist. Let's go ahead and actually fill in that big fact. The left and right sided limits must match for the limit to exist. Okay, and this is just a more specific way to describe a function rather than just saying, okay, well, there is no limit at negative 5. This lets me know specifically what's going on one side and what's going on the other, and why does this thing not have a limit at negative 5. In this next spot, at positive 5, here's the situation. The limit as x approaches 5 from the negative side, or from the left, of the function f equals 3. As I come in on this portion of the graph, following the function, as I get closer and closer to 5 in the x direction, my height is approaching positive 3. Remember, I don't care about this dot up here. I don't care if it's defined, undefined, defined at some other point. Irrelevant. The only thing that matters is where's my green line approaching. Okay, so now as I come in from the other side, also approaching a height of 3. The limit as x goes to 5 from the positive side of f of x, also 3. And that match right there is what allows my limit to exist. Limit as x approaches 5 of f of x equals 3. If this one and this one don't match, it doesn't exist. If this one and this one do match, then that's the limit. And this is just a more technical, mathematical way to say what we've already said in previous videos, which is they've got to be approaching the same number in order for the limit to exist. All right, let's wrap this up with continuity. The more how you should remember it definition of continuity is if you can draw it without lifting up your pencil. Technically, the definition of continuity is this. A function is continuous if the limit as x approaches c from the left of that function, and c could be any particular x value, is equal to the limit as x approaches c from the right, which is what we just talked about on the last slide. The limit from the left and the right have to be equal. And in order for it to be continuous, this also has to be the value of the function at c. Okay, so this is not continuous for a couple of reasons. Number one, the limit from the left is not equal to the limit from the right. The value is the limit from the right. The limit from the right, let's say this is -1. The limit as you come in from the right is -1. The value of the function, because my circle is filled in right there, is -1. But the limit from the left is not. It's +2 or whatever. So this is not continuous. And it's obviously not continuous by just our can I draw it without lifting up my pencil method. This also not continuous because, again, I can't draw it without lifting up my pencil, but technically the limit from the left, the limit from the right are the same, but the value of the function, here's the limit, whatever that height is, the value is not the same. The value is up here. So the limit exists, but it's not continuous. Okay, in order for a function to be continuous, it has to just be going on smoothly, and let's just pick an x value here. The limit from the left, say that's -1. The limit from the left is -1. The limit from the right is -1, and the value of the function also -1. It's not an open hole, it's not a hole filled in somewhere else. This is the definition of continuity. And it's important that you understand the drawing without lifting up your pencil, but occasionally you might come across something where you need to prove something is continuous, and this is the way you do that. You will say limit from left equals limit from right equals value of the function.